So far, when finding rotational dynamics of rigid bodies, we've always applied Euler's second law in this form, where we say that the time derivative, as observed in the inertial reference frame, of the angular momentum about the center of mass is equal to the moment about the center of mass. And this is really useful when we have the kinematics about the center of mass, and we know everything about the center of mass, but sometimes this is actually kind of cumbersome. So what we're going to do is we're going to develop a more generalized expression of Euler's second law using an arbitrary point Q. So we're going to draw from what we know about multi-particle systems to develop these new generalized expressions. So we're going to find the angular momentum about some point Q. And we have a multi-particle system here. And I've only drawn three particles or three masses in this system because we've defined a rigid body as three masses that are non-collinear and have equal spacing between each other no matter what. And so we can even draw our rigid body here. It doesn't matter what it looks like, but it's a sum of all these particles. Now, from a multi-particle system in Chapter 7, we developed this expression, which is the time derivative of the angular momentum about an arbitrary point Q is equal to the moment about Q, and these are due to all the external forces. And then we have this term, and we called this term the inertial moment. And what the inertial moment does is it now considers the acceleration of the point Q as observed in the inertial reference frame. And so by considering that acceleration, we now have this relationship which is buried. This was Newton's second law that's buried in this term. And so remember, we've developed all of our rigid body dynamics from this multi-particle idea. And so what's really nice is that this expression holds very nicely, or it holds true for rigid bodies. And so look at these terms where we have the position vector of Q with respect to G, and then the acceleration of Q with respect to O, which would be the second time differentiation of R of Q with respect to O. And so we're able to determine all of our kinematics from this and plug it into this equation. Now, one problem that we have, now that we've moved on to rigid bodies, is that we can certainly calculate all of these portions here because it's a position vector, and then apply the transport equation a couple times to get the acceleration. But we haven't discussed how to calculate the angular momentum about any point except for the center of mass. And so what we'll see in a moment is that the angular momentum about an arbitrary point, we can relate that to the angular momentum about the center of mass, and then that allows us to insert it into this generalized equation, which includes Euler's second law. So let's start by calculating the angular momentum about our arbitrary point Q in a multi-particle system. And so we did this by just saying the angular momentum about point Q is equal to the sum from 1 to n, in this case 1 to 3, of r I with respect to Q crossed with the mass of each particle multiplied times the velocity with respect to Q. And so this is where we have our position vectors of r of I with respect to Q, and then the velocity of I with respect to Q would be the second time derivative of each of those position vectors. So keeping in mind that we're looking to relate the angular momentum of the center of mass to the angular momentum about Q, let's define two more vectors. So we have r of the center of mass G with respect to Q, and then we have another vector which will go to each of the particles. So this would be r of I with respect to the center of mass. And we define r of I with respect to Q, which we're using in our expression, as the position vector from the center of mass with respect to Q plus the position vector of each particle with respect to the center of mass. Likewise, our velocity, I with respect to Q, which we have in our expression as well, is equal to, it's in the inertial reference frame, is equal to the velocity of the center of mass with respect to Q, as observed in the inertial reference frame, plus the velocity of each particle with respect to the center of mass, as observed in the inertial reference frame. So we're simply using our vector triads to relate this to the center of mass. So then substitute these two expressions into our expression for our angular momentum about the arbitrary point Q. And so here's our first expression, and then cross product with the mass, sum of the masses, and then here's our second expression. And then let's work through each of the cross products. We're going to end up with 4 terms. And for the first term, it's our position vector of g with respect to q, cross with, we include our mass, multiplied times our velocity of g with respect to q. In our second term, we'll take the second part of our position vector and cross it with the mass times the velocity of g with respect to q to get this term. For our third term, it's the position vector of g with respect to q crossed with the mass multiplied times the velocity of each individual mass with respect to g. And then the final and fourth term is the summation of the position vector of I with respect to g crossed with the mass and the velocity of I with respect to g. So we'll take each of these 4 terms and see how we can simplify this into a much nicer expression. So in our first term, we see that our summation only affects the mass. And so when we sum the masses across all the particles, we get the expression of mg and then multiplied by r of g with respect to q cross with the velocity of g with respect to q as observed in the inertial reference frame. Now, to be consistent with how this is presented in the book, we'll stick a couple negative signs in front of this. So it's negative g with respect to q cross with the velocity of the negative velocity of g with respect to q as observed in the inertial reference frame. And this gives us the expression mg, and it's r of q with respect to g crossed with the velocity of q with respect to g. So for our second term, we can rewrite this expression such that we have the summation across all the masses of I with respect to the center of mass multiplied times each mass crossed with the velocity of g with respect to q. And what's nice here is that our first term is equal to 0. And we get this from our center of mass corollary, which we have the balance of all the masses about the center of mass is equal to 0. And now taking a look at our third term, we can rewrite this expression by removing our position vector g with respect to q, and now taking the cross product of the summation of I is equal to 1 to n of mi multiplied times the velocity of I with respect to g. And now we pull out our time derivative, so we have our cross product of our position vector g with respect to q. So this is cross product with our time derivative as observed in the inertial reference frame of the summation of 1 to n of mi of r, I with respect to g. And so we apply our same center of mass corollary where the summation of this moment r multiplied times each mass about the center of mass is equal to 0. So our third term also goes to 0. And for our last term, which is the summation of the position vector of each particle, or each mass with respect to the center of mass, crossed with the mass multiplied times the velocity of each mass with respect to the center of mass, we see that this is simply the angular momentum about the center of mass as observed in the inertial reference frame. And so now we can write our final expression. This is the expression for the angular momentum about some arbitrary point q that's moving. And this is equal to the angular momentum as observed in the inertial reference frame of the center of mass, which we know how to calculate. It's the moment of inertia multiplied times the angular velocity of the rigid body. And then our slop factor, or what relates these two, is the mass of the rigid body multiplied times the position vector of q with respect to g crossed with the velocity of q with respect to g as observed in the inertial reference frame. And so now we have the most generic form of Euler's second law and a way to solve it. So we have the time derivative of the angular momentum about any point that we choose. So this point can be moving, it can be fixed, it can be the center of mass, and it's going to be equal to the moment about that point due to all the external forces on the rigid body plus this inertial moment term. And now we can calculate the angular momentum about that arbitrary point by starting with the angular momentum about the center of mass, which we know is equal to the moment of inertia about the center of mass multiplied times the angular velocity of the body as observed in the inertial reference frame. And then add this term, which connects the two, which is the mass of the rigid body multiplied times the cross product, r of q with respect to the center of mass crossed with the velocity of q with respect to the center of mass. And with this tool, we can work any rotational degree of freedom and solve for the equation of motion